A lot of the times people jump on forums and they'll have learnt from someone who set it up 10 years ago that they set their lash 3 thou looser than the recommended lash setting, and that went better. That's not good advice at all.
Welcome to the HPA Tuned In podcast. I'm Andre, your host, and in this episode, we're joined by Thomas from Goatley of Cams right here in New Zealand. Our aftermarket camshafts are an obvious path to go down when you're trying to extract more power out of just about any engine. However, there's a lot of misconceptions, a lot of misunderstanding about selecting a cam that's going to be right for your application. And one of the most common things I see people doing when they're choosing cams is simply going for the biggest, baddest cam that a particular manufacturer offers, and then finding that A, it doesn't actually work in their otherwise standard engine combination, and B, it turns what was a nice car to drive on the street into an absolute dog. So there's a lot that goes into choosing a cam that's going to suit your particular engine combination and actually give you what you want in terms of drivability, be it a modified street car or perhaps you're building a drag car, maybe a road race car. There's a lot of differences and subtle aspects to those different applications that need to be taken in when selecting your cam. In this episode, we dive deep into the world of camshaft design, and we talk about the aspects of cam terminology that you may have heard and maybe didn't understand, such as duration, advertised duration, lift, lobe, separation, angle, just to name a few. We talk about the different ways that aftermarket camshafts can be made as well, from the likes of a billet, from a cast core, even from grinding down the base circle on an existing factory cam or building up the lobes. And we'll talk about why we would choose one over the other and the pros and cons. We also talk in this episode about cam timing, the importance of the cam timing to making sure that your cam offers the results that you should be expecting, and just as importantly, make sure that you don't end up with your pistons hitting your valves. Before we get into our interview with Thomas, just a quick introduction for those who are new to the podcast. High Performance Academy is an online training school. We specialize in teaching people how to build high performance engines, how to tune aftermarket and factory engine management systems. We also cover motorsport wiring, race, driver education, car setup, data analysis and fabrication. Relevant to today's topic, we do have a course specifically about installing and degreeing an aftermarket camshaft. This is our How to Degree a Cam course. This is a very misunderstood topic, even among a lot of really well-educated mechanics. It's not something that necessarily you're going to be doing if you're used to working on factory engines. But as I just mentioned, getting the cam degreed properly to the manufacturer's spec card is absolutely critical to get the performance out of the cam and ensure reliability. This particular course will give you all of the terminology, some of which we talk about in today's interview, and you'll learn a step-by-step process that you can apply to degreeing a cam in any engine, regardless whether it's a simple pushrod V8 or maybe it's a quad cam V12. It absolutely does not matter. We also include a library of worked examples where you can watch the step-by-step process being applied from start to finish. We'll put a link to that specific course in the show notes, and as a podcast listener, you can use the coupon code podcast75 to get $75 off the purchase of your very first HPA course. And with that How to Degree a Cam course, that is $49 US, so you're going to get that for free. Again, link in the description. All right, enough with our introduction. Let's get into our chat with Thomas now. All right, welcome to the podcast, Thomas. Thanks for joining us today. Now, I want to get started, as we usually do, by just finding out a little bit more about your background, how you got into the automotive industry in the first place. So can you fill us in a little bit?
So I grew up on a little farm down south by the Catlins. Then it was just as a kid, always enjoyed mechanical systems and engineering and, the tractors and machinery and that sort of thing. And then ended up after school coming up to the University of Canterbury here for engineering. Did a year of that and realised I wanted to be in a much more practical role than what that style usually is. So did my trade course with Air New Zealand, and that was a real good hands-on course. and then from there, got a job here at Calford, seeing the advert up for a machinist role. Started in here grinding camshafts on a manual grinder, and after a couple of years of that, moved on to running the CNC, and then running the research and design development department here at Calford, along with a real cool team of guys building camshafts and making race cars and jet boats go fast, basically.
Okay. That's a pretty quick progression straight into the role. So let's just sort of jump back a little bit. You mentioned you did an engineering degree at University of Canterbury. So does what you learned in that degree get put into action with your current role? I mean, you mentioned you wanted a more practical, hands-on sort of approach, but yeah, I'm just interested.
With the design and development side of things, there's the computer skills and the CAD skills that you learn, as well as with designing a lobe and looking at the various lift and velocity and acceleration. It's basically your calculus that you learn at school. Actually, I'm one of the few people that they ask at school, when are you ever going to use this? And I'm like on a daily basis using this exact principles. To look at the various characteristics of how a valve train's going to behave.
Okay, so it's good to know that at least 0.1% of the population out there are actually using calculus. So for the rest of us, not so useful.
It's very much a very practical application of applied mathematics. Yeah.
Okay, so you would say that you basically have to be a mathematical genius to design and develop camshafts?
Oh, I wouldn't go quite that far, but yeah, it does require a bit of a bit of understanding of how that works. But for the most part, we've got good visuals as well that you can really get that through the software. You can see well what you're doing. So it's been cool. It's been good to
We're
learn.
going to dive more obviously into the camshaft design and the software that you just mentioned there as we go through this. But before we sort of go a bit deeper, the time you spent in New Zealand, I mean, I am a pilot myself. I don't fly for airlines, but I haven't seen too many camshafts in a turbine jet engine. So what specifically were you doing for Air New Zealand?
No, so I did the mechanical trade course, and that we went through. So you learn all of your riveting and sheet forming, and but then you do a mechanical course as well. So we got an old VW Beetle Flat 4, which is very similar to the Lycoming and Continental engines that the R22s and like the little Piper aircraft run, and we stripped that completely down and cleaned it up, and then put it all back together and had to put it on the test engine and have it fire up. And that was one of your courses that you had to do as a team of two. So that was real cool for some hands-on bit of mechanical engineering. And yeah, throughout the course you learn a bit of aircraft grade wiring as well. And yeah, those fabrication techniques and mechanical aptitude you picked up has been helpful moving on, and realizing that I did definitely enjoy that mechanical side of things, and then getting a job here with Calford and knowing it was the right sort of way I wanted to go.
Having the opportunity to talk to a handful of sort of aircraft engineers over the years, do you think there's sort of a benefit in learning from that particular industry? Because obviously with aircraft, if something fails, you don't get to pull across to the side of the sky and get out and wait for a tow truck to come and fix it. So I believe there's going to be a higher level of precision and kind of double checking, I guess, that's required to really ensure that everything is 100% and the chances of failure are absolutely minimal. I don't think we see that in the automotive industry. And I mean, of course, not everywhere, but in general, I think it's maybe not seen as so mission critical.
It's a bit of both. A higher level of QC and procedure. Their disciplines are much higher, but also they tend to design with a good window of safety. So you've got that to work with. As much as tight as you have to be, you're hundreds of percentage over how strong it needs to be and how safe it needs to be. So they do it well for both ends, you know. But yeah, that discipline was great to learn for actually having to follow stuff to the book. And if you missed one step, they just you don't get signed off.
Yeah, I think discipline was probably the term I was struggling to actually find there. I mean, for me, going through my private pilot's license and flying general aviation aircraft like Piper Cherokees and Cessna 172s with the Lycoming or Continental engines, it always frustrated me. Obviously, with my automotive background, I mean, these engines, the technology is not there. They rev to sort of 2,500 RPM. They are not economical. They don't make much power. So for me, that's a frustration. The one and only thing that they do seem to do, though, is go just about forever. They are reliable, and of course, you know, if you're stacking your priorities for an aircraft, that reliability really does need to come before everything else. But we digress. Let's get back to cars. Now, I'm interested, do you personally have a passion for race cars, for road cars, or is it all for the customers at these days?
Yeah, no, absolutely. My main passion is for engineering, mechanical systems. So I loved aircrafts and that sort of thing growing up, and cars and race cars, and just seeing what the human mind can come up with for a solution for another engineering problem when you're coming at from all the different directions that you can. I've got, in terms of my own car, I've got an old Mitsubishi Sigma that I'm doing up. So some people would say it's not the most exciting thing, but it's been a labor of the last 5-8 years or something, slowly building that up and building my engine to go with it. So I'd absolutely enjoy cars and enjoy race cars, but haven't yet had my own completed race car project to get too excited about. But that's happening. That's in the works.
That does seem to be the way a lot of projects go. And I mean, I think it would be very unusual to get to the position you're in without some level of passion for motorsport. I think the two kind of go hand in hand. And moving into camshafts, I think this is sort of one of those areas where a lot of enthusiasts kind of get confused. There's a lot of misinformation out there, particularly if you're on forums or Facebook groups about what cams do what. And I think there's sort of a lot of maybe smoke and mirrors around this industry as well. I know one of the approaches that seems sensible if you're uninitiated and don't know much about cams is, all right, I'm building my engine up, so I want a camshaft profile for this engine. Go to the relevant camshaft manufacturer's catalogue and just scroll all the way down to the bottom and get the biggest, baddest, ugliest cam with the biggest numbers and think that that's going to set you up for the best results. Now, as we'll find out today, obviously that's not the case, and camshaft design and specifications are very specific to an application, and get that wrong and you're just going to end up with essentially a slug that's horrible to drive. Is that about right at a very high level?
Yeah, that's about the case, and we do get that quite often. People just want the biggest one or the lumpiest one, or they want to have that number or that advertised number to be able to spout that they've put in their car, whereas in reality that's not going to be a good mix for their engine. And if you go too big, you're going to find that you're just wasting power out the exhaust instead of putting it on the crank where it wants to be. And yes, it'll be loud, but it'll be slow, and you'll actually lose power and efficiency for zero gain, really. So yeah, the camshaft, typically for a lot of locations, it's better to aim for the slightly on the low side on the camshaft and slightly on the high side on the turbo. And that can be sort of the safe way if you don't know what you're doing.
Okay. And I mean, most people without a massive race team budget don't have the ability to go through and try 4 or 5 different cam profiles and maybe 4 or 5 different turbos in their combination. So it is a case of making educated decisions about these parts and relying on advice from the likes of yourself. Now, before we go too much further into this, though, I think it's probably good to sort of come back and get a high-level overview of the camshaft's job. And I mean, obviously, on face value, it seems pretty simple. It's there to open and close the intake and the exhaust valves, which is fine. There's a few bits and pieces between the camshaft and the actual valve, usually, that we'll talk about as well. But there's also a bit of terminology around the camshaft. Now, here, obviously, the podcast, we don't have the ability to have some nice graphics that really simply explain this, but we'll do our best. And I want to sort of go through some of the terminology, and we'll start with timing and cam timing specifically. So obviously getting the cam into the engine is one thing, but it's also quite critical whereabouts the cam is timed relative to the crankshaft rotation so that the intake and exhaust valves are opening and closing at the points that they're designed to. So what does that actually mean? What are the numbers we're looking at here?
Yeah, you touched on that well there. The timing is there to control the 4 valve events: intake opening, intake closing, exhaust opening, exhaust closing. And when we're designing a camshaft, that's where we'll start. Those 4 events basically set up the characteristics for how the engine's going to breathe and how it's going to behave. We start with intake valve closing typically. If we pull that a bit earlier, we're going to have more dynamic compression, but less time for the intake charge to actually get in there. And in a sense, it suits lower RPM and better torque. Whereas if you push that intake valve closing a bit later, you're going to have more chance for air at high RPM, where it's got that ram effect from flowing in fast to actually get in there. Even though the valve's closing after bottom dead center, that mass of air will keep moving in. And so you start setting up these events, and your timing number is, after you've set your intake valve closing and your intake valve opening, it's the degrees between those 2 points, is going to be your advertised duration or your advertised timing, which will be something like 272 degrees, which you'll hear on a typical turbo grind. I've got 272 cams.
Let's talk about that number in a moment. But before we do there, just what you mentioned there, I think, again, if you've not dealt with these before, it's hard to get that concept that air actually has a mass to it. So because of that, there is that tendency to get that ram effect with basically the stack of air in the intake port at high RPM. It's got that momentum. It wants to continue into the cylinder, even against sort of a small amount of pressure in the cylinder. So there's an advantage there at higher RPM from holding the intake valve open a little bit longer.
Yeah, and we can, with a good port and a well-designed valve and the system at RPM, you can see, 120, 130% volumetric efficiency out of those when they're really going on song, and you've got the rest of your tuned lengths happening as well. So being a fluid in a pipe like that, it's acting like a musical instrument and causing those harmonic vibrations up and down the length of the tube. And when we're, especially for, this is NA stuff, but that's, the best place to start when designing a camshaft. You're going to time those events so that those pressure waves reflect back and assist each other. And that's where you get your power band in a high revving, naturally aspirated engine. And then the second thing you're going to look at there is your exhaust valve opening. So you're pulling when you're going to let your gases off the piston in a high RPM engine, you're going to want to open it earlier because you get a signal lag. It's a gas again, so you open the valve and it's not going to react to that for 10, 20 degrees, depending on your RPM, And so you want to keep that pressure on the piston for as long as possible, while also not waiting so long that you've got no energy to get the gases out the exhaust. And yeah, it's a balancing act. It's a lot of learning and know how to work out based on the setup and based on the rest of the engine, how you're going to want those events to act together, and where your restrictions are. Sometimes you can only package an exhaust so well, so you've just got to have more timing in it to get those gases out because they're not going to flow easily.
All right. I think on face value, what we would have assumed is that for the likes of our intake valve opening, we would simply open that valve right bang smack at top dead center when the piston is about to begin the intake stroke, where it's moving from the top of the stroke to the bottom of the stroke.
Yep.
That would make sense, right? Yep. And then, of course, we would then close the intake valve right at the bottom of the stroke before it starts moving up on the compression stroke. And exactly the same way, we would open the exhaust valve at the bottom of the power stroke just as the piston's about to go back up, and then we'd close it at the top. Now, you've already sort of alluded to that's absolutely not the case.
No.
And is this to do with that tuned effect plus the inertia that the mass of the air has?
Yeah, it's to do with that, and it's to do with, you want to actually let that intake charge start flowing into the chamber while the exhaust gases are still heading out. We call that event overlap, and that's where you've got your intake and exhaust open at the same time, and the energy of the exhaust still leaving the pipe and out the headers is going to suck some intake in, and in an ideal system suck a little bit out past the exhaust valve, and then we get that reflective wave from the exhaust pipe, push that back into the chamber just as the exhaust valve closes, and then we've got a real nice homogeneous charge in there that's going to have no exhaust gases left, or the minimal amount for that cylinder head design.
Okay.
And then it carries on with the intake event, with the piston moving down the bore now. And yeah, so intake valve closing and those overlap events, that sets it up for that scavenge event, which can be absolutely massive at the right RPM. But once again, when you got engines that you've tuned to do this, you're going to find real peaky low numbers out down through 3,000-4,000 RPM, and really be sitting on that. It's going to be at that high RPM that they come on song, and that's when you'll see the big drag cars with their individual intakes with the standoff cloud at idle, because they're that scavenge event, the exhaust is coming back up into the chamber, and it's not until they're at RPM that they really come on song. But designing a camshaft for that is why, same switching back to what you said before, why when you don't want to go too big if you're not set up for it.
This is a bit off the topic of terminology, but it's probably a good time to dive off into this, because again, I think it's that uninitiated sort of idea that, bigger is better. And what you've just been talking about hopefully is already started to solidify that we can't look at the camshaft in isolation.
No.
It has to be considered as a complete package, particularly, naturally aspirated engines clearly are more sensitive to all of these elements. So let's not worry about forced induction for the moment. But you've got the intake trumpet, the length of that, as you mentioned, that has to be tuned, or there is a tuning effect that comes from getting that right, which can help get more air into the cylinder. We've got that scavenging effect from the exhaust system, and that really comes down as well to the design of the header, how that's been specified and fabricated. And then, of course, on top of that, there's likes of the head flow, so port work, valve size. So all of these elements come into play, which is why one of the other questions we get, not specifically related to camshaft profiles, is, I've got my factory engine with a 7,000 RPM rev limit. Can I rev that to 10,000 RPM and make more power? And I mean, if you've just looked at the power curve on a dyno from that stock engine, the clear answer is no, because by the factory rev limit, we're already seeing the torque well and truly falling off a cliff, and it's just going to continue to dive, and our power's normally nosed over probably at least 500 RPM earlier. So if we go to 10,000 RPM without making relevant changes, all you're going to do, other than breaking a whole lot of bits, is make next to no power. So then it comes into in order to actually get that engine to perform at 10,000 RPM, what we need to do is basically make the head flow at that higher RPM range, and then work in with a camshaft profile that works with those parts. So I just wanted to clarify that it's not the ability to look at a part in isolation. Everything has to be selected, and I assume you're dealing with your customers, particularly with these high-end projects like we've just been talking about there, to make sure that all of those other parts are up to the task so that the camshaft can actually perform.
Yeah, that's absolutely the case. And we've got a real good team of guys here with some good technical knowledge that will absolutely help when people have those questions, and a good form online too for when you want to put all that data in, and we can help you pick a suitable camshaft, or tell you actually that is not going to work for your engine, or that package, just what you're asking it to do, is physically not possible. And ideally, when I'm designing something, the camshaft it'll sort of be the last bit of the equation. You work out what your other limiting factors are, and then design the cam that's going to best suit that setup. But also, having known how that valve train is set up and what its limiting factors are too, can give you a good point to. You can obviously design an engine that, I want this to do. I've done everything to suit 13,000 RPM, and all of my runners and everything and my piston, my crank can do that, and your valve train can't. I'm not going to be able to do that with a cylinder head. So you want to know that you're not over-engineering for an engine that essentially has its own limitations.
So there you're talking about a valve train design that, no matter essentially what you did with the cam and the valve springs, etc., just could not sustain that sort of RPM reliably.
Yeah, some of them just can't.
Okay.
Some of those your single overhead cam stuff, that you're not going to be able to do it. It's not going to have a big fat rocker arm like that. It just is not going to be able to handle those stresses at that high RPM. But yeah, that's when you can look at bespoke stuff, or swap your cylinder head out, find something better. But yeah, you try and start with a package that you know what your goal is, and then work out if you can build that around that engine, and then yeah, the camshaft and the events that we were talking about is sort of the last thing that you get right once oh, I had to have it was a restricted class, or yeah, I couldn't package my exhaust the way I had to. The turbo only fits this size, all that sort of thing.
Just coming back to the online form that you just mentioned, yeah, what sort of information does a customer need to be able to provide ideally? And again, let's just stick to the sort of high-end naturally aspirated format for the moment. Yeah, what sort of information is required in order for you to be able to do the job as well as possible?
Typically, we'll ask them what application it's going to be running in, whether it's rally or drag or a street thing that they're going to be driving, and then we want to know what fuel they're going to be running, because that's important for how the gases are going to want to behave through the combustion cycle, and that can help determine what size lobes you're going to need. And then what RPM, and obviously we're talking about naturally aspirated, but also we'll look at specifically for naturally aspirated, the chassis, like the weight of the vehicle it's going to be in and the gear ratios, so we can see if it's going to need to be a tight RPM band that it's going to want to run in, or whether we have to go a bit wider, in which case we'll design the cam to suit. Because if you've got something that's got a tall gear ratio and just 4 gears, we're going to not want to give him a 1000 RPM range that his engine's going to run on, or he's never going to get out of the corners.
Yeah, okay. Yeah, that makes sense. And obviously, if you're going to be using a wide ratio in your gear and fall off that sort of power band, it doesn't matter how much the peak power is if it's not actually getting there and it's not usable.
No.
In terms of other things like the actual head flow, exhaust design, and things like trumpet length, those don't come into play here. Is that something you're sort of working backwards and forwards with the customer on?
For most of the guys that are going to approach us through that form are going to be looking for a catalogue option. We have a much more in-depth one that we would go into for that if it's a big circuit racer or something, and then yeah, you're going to ask for what harmonic they're aiming for in their tuned length intakes and what valve size they're going to run. And usually they'll have a flow bench sheet to supply for us too. And once you're there, yeah, you're going to start designing a custom thing, starting with these valve timings and lift right from scratch.
Okay.
For something like that. They're typically not going to be going to the catalogue anymore.
Yeah, that makes sense. Just something that I wanted to mention here. This actually was a Calford car that I tuned years and years and years ago for the old owner of Calford, which was the little Honda drag Civic, and
yes.
I think it was a H22A from memory in it. I'm not sure.
Yeah, we've still got it. It's getting a second cylinder head ported as we speak, I think.
Right. The bit that sticks in mind and why I raise this is I just want to talk about how sensitive these high-end naturally aspirated engines are to something seemingly as insignificant as what I'm about to tell you about, which is a part of the exhaust system. I had that car for an ECU swap, which really doesn't matter too much for the purpose of the story, but I'd run it up on my dyno and got a baseline so that I could get some kind of comparison once I'd done this ECU swap. And we swapped in the ECU, and one of the first tasks you have to do, of course, is set the base timing. And to do that, I was in there with a timing light right down by the crank pulley, and because this is a dedicated drag car, it awkwardly had the headers basically exiting right out essentially in my face. So what I did...
Yep.
Just so that I wasn't getting exhaust gas, some pretty noxious exhaust gas blowing straight in my face while I was doing this with the timing light, is I temporarily tacked, I think it was maybe a 45-degree piece of a U-bend just onto the exhaust tip. That was all it was. It was probably no more than a few inches long and just through 45 degrees. Same diameter, and it was just tacked in like 3 places, so it wasn't fully welded. And anyway, because it was convenient, I left that on the engine while I started tuning it. And when I'd completed the tune, it wasn't stacking up, and an overlay directly with the baseline, the entire shape of the power curve was just dramatically different. And you wouldn't expect to necessarily see that, tune related, you're probably still going to follow in the same broad shape, because that's essentially the volumetric efficiency of the engine. So I sort of went back, scratched my head and thought, well, shit, the only thing I've done here is tack this little extension on. So I cut through my 3 little tack welds, ran it up, and the whole shape of the power curve was back to where it was on the baseline. So unrelated specifically to our conversation, but just how sensitive these naturally aspirated engines can be to something like that. It is really important, particularly when you're trying to do a back-to-back comparison.
No, that's absolutely true, and I'd suspect it was the that scavenge event that we were talking about earlier, where that pressure wave comes from the tip of the exhaust there, and having a 45 instead of a 90 to the flow of gases would have been essentially like a wee baloney cut, where you get 12 or 13 mini waves instead of one big one, and that would have changed it from being a single RPM it was looking at to a more broad
Yep.
torque curve, I'd suspect, but not having that peak that it had.
Yeah.
Yeah, it would change it quite considerably. Yeah, and those are aspects that once you get to the level that you're doing a big naturally aspirated thing, you're looking at all those little fine details and trying to really tune all those out.
This is one of those things that if I had not seen it with my own eyes on my own dyno, I wouldn't have believed it. It was that dramatic for such a subtle change. Anyway, we'll get back to our terminology because we didn't really get too far through this. So when we were talking about timing events on the cam, we've talked about what you're really meaning there, sort of intake valve opening and closing, exhaust valve opening and closing. But there's also different ways of specifying the cam timing, and generally we've got sort of advertised, we've got lift at 50 thousandths of an inch or 1 millimeter if we want to do the metric equivalent, or it's not quite the equivalent, which is actually important here. So why do we use these three different ways of sort of specifying some of the valve events?
It's partially historic. It's the way that the pioneers of cam grinding like Harvey Crane and stuff, they came up with ways just to spec how a cam would be described, and once it becomes the standard nomenclature, it's hard to shake off, which is why even a lot of the old boys going to 1 mil instead of 50 thou is a big challenge at times. But so basically what it is telling you once you set your cam timing, where those events are going to be. So on our cam card, we'll have our advertised duration of 300 degrees, say, and then it'll say that the intake valve opening is going to be 30 degrees before top dead center. And that way, when you go to time up your engine, and the best way to do it is to get that dial indicator on the retainer if it's valve timing, and see that that's where that intake valve opening event happens. You'll always get dwell and lag over the nose. So looking at the intake centerline number, which talks about peak lift, is a good quick check, but it's not near as accurate as seeing those advertised timing numbers, or at 1 mil numbers, which are just basically a similar thing, but they get you away from the ramps. They get you up onto the flank of the lobe. So when we talk about ramps, we're talking about the lash ramp down at the end for seating and take up of your valve, but that gets you up onto the flank where the valve is well and truly open. You've got no lash in the system, and it's going to be very consistent. You'll be able to come around on your timing wheel and see those same numbers to within half a degree every time, and set it up and exactly to the cam card. So just a really good check to see that your timings are in the right place, as well as they're a good indication of how big your lobe is. So once you get your head around you're at 50 cam numbers and know that 220 to 230 is sort of a good street grind, and your 240s to 260s are your big racing cams, then you can just see at a glance that, this is going to be much too big for my application, or I'm kind of in the ballpark, which is why that's hung around and been just a useful number to look at.
Now, you kind of talk through this, but I just want to come back and just really sort of crystallize this. Most people would think, well, if I've got 300 degree advertised duration, you could time off those numbers. Basically, like, well, let's look at when the intake valve first starts to move off its seat, and that's our intake valve opening, which, I mean, of course, yes, that is the case, but we don't do that. We instead time at 50 thou lift, and you've sort of explained that's because we're on the flank of the cam there. We're getting nice consistent results. And the bit that's easy to overlook is if you're trying to find that point with your dial gauge where that valve very first starts to open because of that take up of the lash, etc., it's very hard to get true consistency, and we might see from one engine cycle to the next, that point might change a few degrees, correct?
Yeah, and in a perfect world, your valve train and your system's going to be infinitely stiff, but that's not the case, and so you're going to start lifting that valve, and your rocker's going to deform slightly, and your spring you got springs that are 150 pounds on that seat. It actually takes some lash out of the system, not just the lash like your valve clearance, but your cam journals are going to push down slightly, and your everything's going to move a little bit. So that can be 3 or 4 degrees of error where you've got dwell, where the cam started to push, but the valve hasn't started to move yet.
Okay, cool. I think we've got that clarified. The other thing you mentioned there was the lobe centerline, and that's one of the specifications for the cam timing on your cam card. But timing to that lobe center line is difficult. You sort of mentioned dwell over the nose of the cam, which obviously doesn't necessarily mean too much if you haven't actually seen that. So it's kind of no different really to finding true top dead center with a dial indicator or something down a spark plug hole. Trying to find that absolute point where the piston is at the very top of the stroke. You can move the crankshaft backwards and forwards probably 5 degrees or so, and you really won't see that dial indicator move. So when we're trying to find TDC, the technique we use there is we'll actually use a positive stop or something, stop the piston a little bit down from TDC, or maybe use our dial indicator and measure 50 thou before TDC on each side of rotation, and then we know TDC is in exactly that location. We split the difference. Now, that is a technique that some people use to degree a cam as well. Rather than looking at the opening and closing events, they'll take maybe 50 thou below peak lift each side of peak lift, split the difference, and then use that as the center line. Now, that's not really the preferred technique, although it'll get you close. Can you explain to us why that might not be perfect in all situations?
But yeah, you could use something like that. It's not something I've heard of very much, but the thing there is, if you wanted to use that technique, essentially you could then work out where your valve center line is relative to TDC, but those numbers aren't going to be anywhere on your cam card, so you're going to have to work it out yourself, and you risk the valve motion not necessarily being a symmetric motion, which a lot of modern engines it will typically aim for something close to symmetric, but in quite a few cases, actually having the valve motion a bit more aggressive on opening or closing can be beneficial to a system. And so when we spec our timings as a cam manufacturer, we'll tell you where to put them at 1 mil lift, because that's where anywhere below 1 mil lift, you're in the signal lag area anyway, and it's a chunk above that really matters for your timings. And if you happen to be like a 5 or 6 degree split up around the nose, you're going to be maybe 10, 15 degrees out down at those 1 mil numbers, because it's not actually symmetrical, and it's not like every old flat tap at V8 where they were.
Yeah, that's the part I really wanted to kind of focus on. I think that on face value, the assumption would be that cam lobe is symmetrical, but as you've clarified there, it's not. So that's why using that technique is going to get you close, but not necessarily right where you need to be. Now, when we're comparing numbers here between, it seems to be predominantly the JDM manufacturers of cams will specify, because they work in metric, duration numbers in 1 millimeter lift. Whereas everywhere else in the world it's 50 thou, which the numbers are close but not quite. If my math is right, I think 50 thou is about 1.27 millimeters. Does that sound about right?
That's correct, yeah.
So a duration number at 50 thou of lift for exactly the same cam profile, that therefore is going to be a smaller number than if we were measuring duration at 1 millimeter?
Yes, the duration at 1 mil will typically be bigger. A lot of the time too, we'll have the at cam will have at 50, because the V8 stuff and your old push rod stuff, they're going to be looking at what the lift is doing, and often not actually looking at what the valve's doing after the rocker, because they can just drop down the push rod tube there, and that's a more convenient way to time it with the head still off. Whereas with your modern overhead cam stuff, you're going to be looking at the valve and the actual valve motion, and in that case, we just find 1 mil lift is what most of the dials read out, and you're working in mils of lift for the valve and everything else, so it just saves the confusion.
Well, all I wanted to really sort of get out of that is just understanding the numbers that you're looking at, because it can be very misleading if you're comparing or any values for that matter, on a cam card at 1 millimeter of lift versus a different cam where it's specified at 50 thou, correct? They're not the same.
Yeah. So there'll be about 10 degrees in it usually on a typical for the aggression of a cam. There'll be approximately like 6 to 10 degrees between 50 and 1 mil, which they're actually the exact same size cam. So if we've got a camshaft that's 230 at 1 mil, it'll be about 222 at 50.
Okay. Just because you've also just mentioned it with your example with the pushrod V8 being able to time the cam with the heads off, which is nice and convenient, and why you're then looking at camshaft numbers versus valve numbers. And I mean, people listening might be sort of thinking to themselves at this point, well, why would the lift at the cam lobe be different to the lift at the valve? So can you just talk us through why that's the case?
Well, on a conventional push rod, you're going to have a rocker ratio or a rocker at the top that transforms your push rod motion to your valve motion, and they're typically 1.5 to 1.8 ratio. So if you've got 300 lift at the cam, you'll have about 500 at the valve total lift. And timing wise, it relates exactly to what the cam's up to, though. So you can time them in knowing what you're doing at the cam, and then bolt your other parts on and know that the valve's behaving relatively to what you told it to do. Whereas in your overhead cam engines, yes, some of them still have slippers and rockers like a RB30 or a H series, so they've got the rocker ratio to multiply by. But a lot of engines are obviously just your flat tappet bucket style where there's no rocker ratio, they're just 1-to-1. In that case, we can just have a 1-to-1 valve motion, and all it does is subtracts your lash if it's got some and isn't hydraulic.
Yeah, I think it's just important to understand that there's obviously a lot of different designs of valve train, and having that rocker multiplication factor in there is quite common. So just understanding that that's an element.
Yeah, and it's important you read the cam manufacturer's specs and make sure you know where they've given those numbers for, whether they're at the cam or at the valve or at the lifter sometimes, and how that relates to how you need to measure them and set them up in your engine. And for some cases, it can be quite a cumbersome thing to do, and like getting a little bent foot around underneath a rocker can be really tricky to get right, but it is what you have to do to get it right.
Yep. All right, next term that I want to dive into, LSA or lobe separation angle. Can you talk us through what that refers to?
Yeah, so lobe separation is essentially the degrees between the intake valve at peak lift and the exhaust valve at peak lift. Your intake centerline and exhaust centerline will be relative to TDC, and then your lobe separation, to work it out, is just the average between those two numbers. So a wider lobe separation is going to have less overlap and less scavenge, and typically be suited for that wider RPM and like towing cams, whereas a tighter lobe separation is going to have that larger overlap event when it's going to be a lumpier idle and better suited for the higher RPM. But also that obviously factors into how big both those lobes are. So you're moving your 4 valve events around, and then they set the lobe separation by proxy. It's the same as your centerline numbers, where they're a good indication once you got your head around a few different packages, but it's as a number is very relative to the rest of the system. So it's sort of something that comes out in the wash. You do the rest of your design and then go, I've got a lobe separation of 112, or that's what it's going to want to have.
Okay. In terms of the cam design, on a pushrod style single cam, that lobe separation angle is obviously sort of baked in during manufacture. There's no ability to change that.
Yeah, and it's a well-known thing, because once you've got your lobes that exist and your catalogue that exists, you might go, I want to pull 2 degrees of lobe separation out because I want it to behave better down low, or I want it to have a lumpier, angrier idle, and that's what I care about. Or it's going in a jet boat, so it's not going to want to rev, so we'll go down from 112 to 110 lobe separation, and then it's only going to rev to 4.5, and that's going to be happier for that and in a better power band.
So again, really just coming down to it's so dependent on the application. You can't say there's a one size fits all. This is the lobe separation angle that you should be running.
No, as a general rule, your naturally aspirated stuff's going to be on a narrower lobe separation than supercharged and turbocharged. But apart from that, it comes down to the two lobes that you're already using, and lobe separation is when you've already got those existing lobes,
Okay.
because it's just not going to be a custom design. You're going to pick two things and then work out where they react well together with each other.
Of course, on a twin cam engine, assuming we've got some adjustability, we can actually tweak advance or retard both of the cams together, which obviously will retain the existing lobe separation angle, but we have the ability to then advance or retard the cams individually, which will then have the knock-on effect of adjusting that LSA, correct?
Absolutely, yeah.
Okay. All right, let's move on and talk a little bit about valve lash. And it's a term you've brought up a couple of times. And again, we've probably got a bunch of listeners who have never heard valve lash. So can you explain what that is and why we need it?
Yeah, so on a mechanical system, meaning one that's not hydraulic, valve lash is the clearance that you'll have between the lifter and the follower, and the cam, sorry. And so that lash is there so that as we run through the different operating temperatures of the engine, there'll always be a bit of clearance to stop basically the valve from being held open at any point, as well as there'll be a ramp shape to that that'll mean that the valve opens nice and gently and closes nice and gently and isn't going to prematurely wear the seat or the other parts in the system or bend things. Basically, it's like hitting it with a hammer if you've got too much lash, and that's gonna break and wear parts. And if you don't have enough lash, your engine's gonna cool down and your valves are gonna be open and you won't be able to start it again. So you're sitting around that 10 to 12 thou range on a lot of overhead cam stuff, and based on the materials of the block and the materials of the engine and how they will thermally grow through the heat cycles, as well as the heat cycles they're going to be sitting at and how long they're going to be held at high temperature, you'll design a lobe and a lash and such to run that. And that's one thing that a lot of the times people jump on forums and they'll have learnt from someone who set it up 10 years ago that they set their lash 3 thou looser than the recommended lash setting, and that went better. That's not a good advice at all. We're always sitting on the high side of lash and going with what the manufacturer suggests, is because they designed a lobe that's specifically set for that. It doesn't matter what your OEM guys were doing, which are often a lot safer than a race lobe. It doesn't matter what engine it is. We've always designed those to be a very tight operating window. Usually they're in about 2 or 3 thou that it actually is running in, and so, or 0.06 of a mil or whatever that is. And so you're going to be needing to follow that cam card closely and stick to those recommended numbers because they are what you need.
Okay, so don't get loose and free with the lash thinking that you know better than the manufacturer.
Basically, you're just risking the longevity of your engine massively, or the performance, because if you set it too tight, you're just going to have a whole lot of extra advertised duration for no gain. It's just going to be a big lazy thing.
Okay, so a couple of elements that I want to dive into here. First of all, that lash, I mean, you've just explained that it is important, and the other element here is when we're actually degreeing a cam initially, that lash needs to be taken into account, because if we haven't got that lash set correctly, then basically all bets are off, because your timing events are based on the lash being set correctly, right? So that's sort of the process we go through. And if I'm right in saying some engines there as well, or some cam profiles, you actually specify degreeing it with 0 lash. Is that correct? Is my memory serve correct?
For like a hydraulic one?
No, for a mechanical. I just had that in the back of my mind. I can't remember if it was maybe a Honda B series that I'd degreed a Calford cam in, and I think obviously it's quick and easy to adjust the lash on the B series, but maybe I'm off on a tangent here and completely wrong.
No, typically no. We'd get you to set it with the correct lash. With something like a B series, you might set it with a very little amount of lash. Then once it gets hot, you're going to run a recheck that, because the lash will likely grow a little bit. And wherever you can, if you can check your lash hot, if it's not a bucket with a shim, which obviously that you can't do much about that, you're going to want to reset it once it heats up, because every configuration based on the valve material and the head and how it's run is going to move slightly different. Yeah, typically there will be a lash setting, and there's the odd time where, well, like the V8s, you're not looking at the lash side of the system, you're looking at the lifter, so you're looking just straight at cam motion. We can ignore lash completely. We're still going to want to set lash correctly out the other side, but your timings you don't have to worry about lash. But the cam card will always tell you what your timings are going to be relative to lash if it's relevant.
Now, in terms of a lot of, or maybe the majority of production engines, sort of moved away from from a solid setup, and I guess it's important to say there are a variety of mechanical valve train designs, be it the B series I just mentioned, where you've got the relatively easy adjustability of the lash, same maybe with a pushrod V8, and then there's the more complex ones where we've got a shim under bucket or something of that nature, which really requires quite a lot more effort to adjust the lash. In terms of pros and cons of that versus hydraulic, well, actually, before we dive into that, just in comparison, can you give us a brief rundown on how a hydraulic system works?
Yeah, so a hydraulic system has a little hydraulic lash adjuster on one side of the rocker or under the bucket, and basically as oil pressure comes in, it'll pump up a little valve inside there and close the lash up, and those are spec'd with the oil pressure to not be enough that they can push against the valve spring or open it, but they'll keep the system always in contact and have zero lash, and that's a benefit in the sense that you've always you don't have to worry about that tappet wear to the same degree. You've got something that's always in contact and always keeping oil moving around that lobe surface as well. It doesn't pull away on the base circle, and that for an OEM manufacturer for longevity is a really good thing, as well as ease of setup. They don't have to worry about someone coming along and lashing up all of their engines. You can just slap them together and run them up with some oil pressure, and they're away. And they'll run like that for basically forever in their OEM configuration.
That's important as well, because when we're talking about these more complex engines with 4 valves per cylinder, it's actually quite a time-consuming process to go through and manually adjust the lash, particularly, again, if it's something a little bit more tricky where there's a shim under bucket or something like that. It's quite a big job, correct?
Yeah, it is, yeah.
Okay, so the hydraulic, on the other hand, is essentially maintenance-free, which is why OEs like it.
Yeah, that's the case, yeah. And it's a heavier system, and it doesn't respond to RPM as well, which is why when you get to your higher revving and higher pressure systems, you're going to want to switch back to a solid lifter, like in your Evo rally cars and stuff. And when you're running a lot of aggressive anti-lag and shift cuts, and you've got that explosion happening back through the exhaust, that's going to prefer to be a solid lifter as well. So it's not trying to pump that hydraulic lifter down, because we can get to a point where we get enough force in there that the oil just doesn't get into the lifter in time at the RPMs, and essentially you pump down your lifters and get a whole lot of lash, which is not nice for the system because they do not have a ramp at all on that lobe design. And so any lash is really hard on the system.
So a good example of what you're just talking about there with the hydraulic just not being suited to the job. Obviously, my background sort of drag racing, and I was a bit of a 4G63 specialist. So they run a conventional in stock form, a hydraulic lash adjuster and a rocker arm, and under normal circumstances, they actually work really, really well, and they don't tend to have too much trouble even at high RPM. But where they absolutely will run into issue is with the larger turbos. We run a 2-step launch control strategy, which is, of course, creating a lot of big pressure pulsations in the exhaust manifold while it's spooling the turbo. And what's easy to overlook is that can and will actually pop the exhaust valve back off its seat, even with pretty significant seat pressures on the springs. And with a hydraulic lash adjuster, as soon as that valve pops back off the spring, pops back off the seat, I should say, the lash adjuster pumps up almost instantly and then holds the exhaust valve open, so you end up losing all compression. So a lot of 4G63 guys and girls will have experienced that. So that's just one of those circumstances where swapping to a mechanical strategy is essential. Shift cut, as you mentioned, does tend to do exactly the same thing. Even the RPM control strategy, if you're using ignition cut versus fuel cut, that will have that same effect. The other thing you mentioned there, which I wanted to focus on, is the ramp on the actual cam profile. There is a difference between a mechanical grind and a hydraulic grind, correct?
Yeah, essentially a mechanical grind, once again, to take up that lash that we need for the thermal growth of the engine, is going to be 16, 18 thou tall ramp, which is just like a nice gentle slope underneath where you'd set lash, and it's trailing down for another 30 or 40 degrees. It's near of the lobe you don't use, but it's there to pick up that lifter and get them moving before it starts to accelerate up the flank. On a hydraulic lash adjusted setup, you don't want that because you basically have 70 degrees of timing where it's just slowly opening the valve and then starts to go. So they basically have maybe a 2 or 3 thou ramp, but we want a little bit just to give the valve a wee bit of time to get off the seat, and not jerk it around too much. But it will have almost no ramp at all. It's just a smooth little design, and a little bit of a closing ramp sometimes just to give the lash adjuster time to catch up on the way down too, because we don't want to bounce the valve. Because like you said, if we as soon as that valve bounces again, that lash adjuster will pump it up and think that's where it wants to be. So we want to just make sure they settle real nicely on the closing side as well. Whereas if you do bounce a valve on a solid lifter thing, as much as it's bad valve control, it's not going to ruin the rest of your valve timing because of the lash, unless you spit a shim or something real bad.
Which is another problem as well.
Yeah. That's where your limitations come to the other side. Something that you can mechanically adjust is very convenient and strong, but it is heavy. You've got another a bolt and adjuster and everything in there, and so when you're at high RPM, that's going to be another bit of force on your spring that you're trying to avoid. So ideally, you go away from those, and every time you can get rid of a shim or another part of the mechanical system, that's another thing that can't fail, basically. And so in your high revving bucket engines, you're going to want to go to a completely shimless setup, but that gets to the point where you need an engine builder that's going to set all of your lash by actually grinding the back of the valves and tipping the valves to be the correct height when he assembles it. And you've got to really know what you're doing then, because even as you're talking a head down, those lashes change and move, and you don't get a second shot at it really.
Yeah. This gets really deep really quickly,
Yeah.
and probably I don't want to go too far down that rabbit hole, but one of the things I give an example of this with our SR20 VE turbo engine. So this is Nissan's P11 Primera VVL cylinder head in our example, and it gets worse when you start using higher strength or larger diameter head studs. But we had the head CNC ported. I hate shimming these heads. It's not my favorite job. Maybe I'm just lazy, but it's definitely not my preferred job. So we had the guy who did the head basically shim everything for us, and that was all set within probably plus or minus 1 thou of where it needed to be, and bolted it down onto the block, and instantly there were about 4 valves that were now outside of spec that needed to be reshimmed, and that's going to be pretty common, and really there's no way around that. So worth just sort of understanding that is something that you do need to take into account. If you go to the bucket and shim style cylinder heads, there's a problem there with that shim maybe bouncing out. So for a lot of the modern engines now, you can buy buckets that are actually a specific thickness. So they essentially do the shimming, and you buy the buckets to get your clearance where you want. So again, that becomes a more costly exercise as well, because instead of buying just a small shim, you're actually buying a complete bucket. But that's the game we're playing, and the advantage, of course, is then there is no shim to fall out. You've got a nice reliable setup, which of course is what we want, particularly at high RPM. Right, let's move back and get back on track here. And the other element that we really can't ignore when we're talking about the camshaft is the valve spring. And this is really, really critical. The valve spring obviously is in charge of sort of controlling that valve motion and preventing sort of the valve running away from the camshaft essentially. And when that happens, some really bad stuff can also come out of that. So what do we need to know here? Is this a case of you will be able to specify the correct valve spring for a particular camshaft that you've produced?
Yeah, absolutely. We always endeavour to make sure we've got a really good, safe valve spring package to go with anything, especially in our catalogue. And we've got a wide range of valve springs to be able to work with anything custom we're going to do. The valve springs, we typically deal with Pack Racing, and they're a very well-tested and well-known brand, and they do a lot of proprietary stuff for us to really go with the applications we're going to be running. But when you're designing a cam, when it comes down to the valve spring, it's about weighing everything in the system, knowing what your locks and your retainer and your follower is all going to be doing, and then looking at the RPM you want to run it to, and seeing that spring is going to be able to handle those dynamic forces at that RPM, as well as it's got a natural frequency, which is going to be safe to those numbers as well. So basically, because the springs, the wire is always going to have a certain frequency where it's going to want to resonate, and the bigger the number, the better, typically.
I assume you have to stay away from that resonant frequency.
Well, the resonant frequency will usually be about 38, 40,000 RPM or cycles per minute, and obviously the camshaft's doing half RPM, so we're only looking at having it C4 or 5,000, but any, once again, harmonic number inside that, so a reflective wave at a seventh of that will have a peak, and so every seventh hit on that spring is going to be cancelled out by the harmonic frequency of the spring, and they'll start to go slack. They'll lose some force at that RPM. And so we have to look at those and see that the amount that they lose isn't going to cause them to lose so much force that it's going to lose control, and so that we can actually rev past that point. And we'll design the lobe to be a certain degree of aggression based on that and a certain degree of force. And sometimes it can be a little bit more lift, making sure the spring's a little bit more compressed is what you need to just have that spring better set up as it comes off the nose to keep this whole system under control. The wee valve spring in an engine is basically the most hard worked part. A lot of the time, it's doing so much to keep everything under control. If anything goes wrong with that, it can be a very expensive learning curve very fast, as I'm sure you're aware.
Yeah, it goes bad pretty quickly, and it normally happens at high RPM where there's not going to be a lot left of your engine, unfortunately.
Yeah, when you're really on the cutting edge, you've got maybe 40 thou of clearance from your valve to your piston at TDC. So if that valve loses control or bounces, it doesn't have to go far.
In terms of valve spring packages for performance cylinder head installations, in the, I call it the older days. I mean, obviously they're still around, but when I was drag racing, the go-to was usually a double valve spring with an inner and an outer spring in order to get a combination that was going to provide the pressure that we needed and also be reliable at the RPM we were running to, which is at that time sort of 10 and a half, 11,000. These days, again, I want to clarify, double and triple valve springs definitely still a thing, but for the mainstream performance applications, if we're not going sort of too far, normally we sort of can get away with a single valve spring and this newer style, maybe again it's not that new now, but beehive valve springs. Can you talk to us about what a beehive valve spring is, why they can sort of in a lot of ways do the job a more sophisticated double valve spring package used to be required for?
Yeah, so it basically swings back to what I was saying before about the natural frequency. But a beehive valve spring will have 7 or 8 coils in them, and the top maybe 2 or 3 will be slightly tighter wound. And what that creates is a higher natural frequency because it essentially has a varying frequency in the wire there. So you've got different natural frequencies on a single spring, which can work together to cancel each other out. From a single spring, you get a much higher number, whereas your old single non-damp springs might have got to 22, 24,000. Your modern beehives will get to 38, 42,000, those sort of numbers quite easily. And that's just that much more safety for RPM. The other benefit being that they're also lighter because you've only got one to deal with. And when you're looking at the mass of a valve train affecting a spring, the mass of the spring itself is a big part of that. It's a rather heavy unit in there, and it's got to fight itself to get moving every time. And then ideally conical springs, which is along the same principle as beehive, but they're getting tighter all the way up, are an even better way to go again. But it's just the packaging of those is so difficult because you get so small at the top end and you still got to fit your locks and your retainer and everything up there that they're typically not enough real estate to actually get them to work. But on paper, that's even a better step up again.
All right. In terms of the valve spring, we've got the same sort of terminology that we need to understand, just like the cam itself. We've got the installed height, we've got seat pressure across the nose, also clearance to coil bind or lift to coil bind. Can you just run us through sort of really briefly what those terms actually mean?
Your installed height is where the spring will be compressed to when it's sitting on the base circle, basically under the retainer with no force from the cam or anything yet. And typically that's where you're going to get your seated force, which will be a lot of the times around that 70 to 80 pound or bigger for racier engines, but you'll see those numbers on your box, and that gives you your point to set the spring up in the head and know that it's going to be keeping everything under control based on the manufacturer's specifications. And then you've got your force, usually X amount of lift, so it might say your force at 11 mil lift, which is what most of the camshafts are going to be, and that'll let you know what it's going to do over the nose of the lobe, and you can check that that's not going to be too heavy for your specific application. But once again, typically we'll be setting that for you and letting you know what's going to work, because that comes down again to camshaft materials and valve train style, or whether it's a bucket or a roller, what it's going to need to keep that under control, and what it can actually take before you start to fail other aspects of the valve train.
Right. So from the perspective of the person installing the valve springs, I guess there's often an assumption that we can just drop this in and it's going to be good to go. But that installed height specification, that's quite important. So we need to go through and check this. And if it's not right, what are our options to get it where it needs to be?
Yeah, you absolutely do need to check this. Typically, the installed height we've spec'd for our valves are what the OEM head will fit them in at. But it's as soon as you've put different valves in, or cut your seats, or swapped your retainer out, that's all changed. So you want to measure what that's going to be by taking all those measurements off the retainer height and off the valve tip height, and then you can see where that spring is going to sit. And it could be 1 or 2 millimeters out, in which case you'll put a thicker seat under the spring, or if it's much too tight, that can be a bit trickier, but you can use offset locks or sink your valves a little bit further to get those back to where they need to be, so that you're not going to be running your springs into coil bind or something, because if you were to set them much too tight, you're just not going to be able to fit your cam lift in before your coils are bound up and solid, and that obviously won't work. So yeah, checking those numbers and checking that they are within the specifications is always a good practice to do.
Yeah, I think there's probably too many people out there just blindly hoping or assuming and putting them in and installing them without these checks, that they're not that time consuming to do, and then you know that you've got what you're supposed to have, and it just avoids any potential sort of problems down the track. So yeah, it's a non-negotiable.
Oh, it absolutely happens, and on the same sort of wavelength, the amount of people that will drop a set of camshafts in and just line the dots up on cam gears, and send it when you've skimmed your head. You've moved a different thickness head gasket that's going to change your bout length on that side and change your timings. All those things are actually timing up off the spec card. You could be a long way out for multiple different mechanical reasons, as well as the fact that we don't even know that cam gears you brought were made to a specification relative to the engine at all. They can be all over the show. So the dots and the adjustable numbers on that are an indication once you time it up and know where they are to move it around.
Yeah, I'm glad that you brought that up, because that is so common. People just installing an aftermarket cam with a vernier adjustable cam gear even, and just lining up on zero and assuming that we're good to go. But no, as you mentioned, there's so many things as a normal practice or normal part of an engine build, having the head and the block skimmed, just for two examples there, that will affect that. So it's a case of always going through the process. It is a little time consuming, but it's not difficult. It doesn't require expensive tools. It's just a little bit of patience and doing the job properly to degree that cam in the first place. And then once you're there, then go to the dyno and you can swing the cam a little bit and see if maybe you can move that power curve around, but at least you're starting from a known base point and where that camshaft manufacturer has decided that cam will work best. Now, another question we quite often get is around the process of cam break-in for a new camshaft, and I think there's a little bit of sort of urban myth going around as to what's required. Quite often we will see as well for a given camshaft manufacturer will have a recommendation, something along the lines of, immediately after startup, rev the engine to sort of 2,500 to 3,500 RPM. Don't hold constant RPM continually. Rev the engine between those points for the first 20 minutes. What's this all about? Is this a requirement for every camshaft, or is it specific to the likes of flat tappet? Yeah, give us some information here.
It's definitely most critical for flat tappet. On a flat tappet engine, it's basically always going to be starting up a bit dry, and because they're a friction setup, they don't have a roller or a bearing in there to take that friction out of the system. They are just going to be rubbing parts, and so they'll be for us a cast iron camshaft with a Parco treatment to them, which is basically a sacrificial lubricative surface, which is designed to wear off in that initial startup while oil gets there. But you do just want to get up onto your RPM and get that oil pressure up into the head as quick as you can, as well as with respect to a cam lobe. The place where it's going to see the highest force is over the nose, and when it's going to see that highest force is going to be at idle at its low RPM, because that's when you don't have any assistance from the valve train moving to actually push against that spring. When you're revving, your lift is going to want to stay in motion and actually try to lift off over the nose, whereas at idle, that full force of the spring is just pushing on that, and it's pushing for a long time, which is where it's going to try and push through that oil layer and push through that shear strength of your oil and break that boundary down. Once metal's touching metal, that's where things aren't going so well. But once you've broken in that surface and got that oil layer going, it can obviously handle idling at that point. But you're trying to break off like those small microscopic layers and let those two surfaces mate so that they'll have the longest chance at survival. And that run-in period is massive. And also running, we'll talk about a high zinc, like ZDDP oil. That's essentially a metal in your oil that will, when there's a small scratch, it'll come into those holes and sacrifice itself again to fill that back in and keep them good, and goes real well with cast iron cams like that.
Okay, so that ZDDP additive, because sometimes you can actually purchase this as an additive as opposed to an oil that is high in that zinc phosphate, I think it is. I'm not an oil specialist here, but so that's a benefit to add in with that style of valve train.
Yeah. Ideally, purchasing an oil that's got it in there in high numbers is the best way. But if you don't have that available based on where you are, then an additive is a good second way to do that. But definitely on your startup and your run-in period, having that zinc to help out with that wear-in process is huge. And back in the day, obviously we had leaded fuels, which did a lot of that for us. But the zinc additive is essentially trying to do what lead used to do, and keeping engines alive.
All right. I think we've clarified that is important for that flat tappet style cam, and probably just as important as well with that style of cam. If you're fitting a new cam, you do not want to be fitting that with an old set of used tappets, lifters. You want to either start with fresh, or is refacing an option? I hear mixed sort of stories about whether refacing is a viable alternative to just replacing them with new.
Refacing is definitely still an option, more for old flat tappet stuff. Like if you pull in your old 4K apart, you can just get those refaced. If you're doing a bucket engine, something like that, the tolerances are a lot tighter, and it's better just to get new ones. Although a lot of the time the OEM follower will still be in really good condition, and that can actually be salvaged. The other thing is a slipper pad, which is what we see in a B series or something like that. They're very prone to wear. They're probably the hardest system to keep together because of the oil entrainment, which is as the cam's coming around, he's trying to drag oil with him, but there'll be a point where as that follower's going down, moving away from the cam, and the cam's coming around, the oil velocity will basically be a net zero. And at that point, you've got one piece of oil just trying to do all the work. And you'll see that on your lifters. Often there'll be like a line where it's worn slightly worse than anywhere else. And so refacing those and making sure those don't have any sharp points or any bad wear like that is going to be crucial to getting a new cam running again, because if there's anywhere that is in a nice radius, it's going to break through that oil shear layer real quick.
Okay. All right. So that's flat tappet for us. What about the break-in techniques for other valve trains? Maybe we've got a roller style lifter and a push rod engine, or maybe sort of a more modern, double overhead cam, multi-valve engine, be that a roller rocker, maybe it's a bucket, cam on bucket. Is it the same break-in process for all of those types of valve train?
In terms of the valve train specifically on a roller, it's not going to have the same sliding wear that you're going to need to worry about. A lot of them are going to be a hydraulic lash adjuster, and in that case, you want to get that RPM up quick to get that oil pressure up as fast as you can. A lot of the times, it's going to sound quite tappety for a couple of minutes while it pumps all those up, and you've got to just grin and bear it in essence. But yeah, with a roller, no, it doesn't have that same level of break in procedure. But typically, it's not that often that all you've done is the camshaft, and so when you've got fresh valves and fresh springs and retainers mating, and just getting everything up to RPM and getting a good solid temperature cycle, like a thermal cycle through that engine, is going to be really good for getting all those parts to mate nicely where they want to go, bed in really well. Even if it's a roller, or regardless of what type of valve train it's got, it's just good practice. Yes, essentially you could probably cut a few corners if you're just doing a roller cam, but for saving 20 minutes, it is a better practice to do it, and take the time.
Where I sort of find the issue sometimes comes in is when you've got a full sort of ground up rebuild of everything. Sometimes the cam break-in process is kind of at odds a little bit with my own preferred engine break-in process. And by this, I'm talking about the process we use to bed the rings. And aside from everything else that's in the engine, really it's the rings is the primary aspect that we're trying to bed against that fresh home pattern of the bores. We've got a relatively limited window that we want to do that, and the process I go through is quite specific. So sometimes that sort of flies a little bit in the face of what we would do purely with the cam, but sometimes we're compromised, and it is to a degree just what it is.
Yeah, that is a bit of a balancing act. Usually once you're at that level, you're going to know your engine and know what it needs, and potentially, depending what it is, you can pull I don't know, pull a valve spring out of a dual spring to take some weight off that valve train while you're bedding in the rest of the engine, or which you might do on a big V8 or something. And you can find ways to make sure that both aspects get the best chance possible.
All right, let's move on to cam design a little bit. So what was the process for this? Is the software that you're using, is that something that is industry standard, or is it a bespoke software that you've developed? Yeah, tell us how that all works out.
No, we have a proprietary software that we've developed. He's a maths professor in Texas now, I think, but we've been dealing with him for a long time, and he does our doctor software, which is used for analysis of cams and lobes and the valve train as a whole, and then also our design software, which is where we'd actually design a valve motion and have the software spit out a corresponding cam design that's going to be used for that. And we've been able to get into that since the mid 2000s when we got our CNC camshaft grinder. Obviously, without one of those, designing a lobe is not much use to you because you can't produce it. But yeah, being able to go down that route has taken Calford as a company major steps forward, and we've since designed some really cool custom stuff for lots of cool vehicles and companies around the world. But yeah, so you'd start with knowing your valve train and knowing your limitations of that valve train. For example, a flat tappet or a bucket engine is straight away limited to the velocity it can run by the size of the bucket. So essentially, the camshaft's acting as a lever that reaches out and pushes down on that bucket. And as it's coming around, the longer that lever is for each degree, the faster it'll push that valve down, if that makes sense. And so you can obviously only reach so far before you're at the edge of the bucket. And so your velocity is limited by the radius of that bucket. And there's no way to fix that. You've got a design constraint that's where you start. And so if I design a lobe that's 260 degrees advertised, I can only be so steep on the flanks. It can't physically be any steeper, or I'm going to wear this valve train out. And so we'll look at all the aspects like that, and if it's a roller, if it's a push rod, if it's a slipper cam, and then we'll put those geometry and design constraints into the software, and then design a valve motion, because that's what we care about. We care about what the valve's doing. The camshaft's just there to make it happen. And so we'll design a valve motion, and then that will take that back through the geometry of the valve train and spit out a lobe that we can grind onto our blanks.
And we'll talk about that process in a moment. In terms of the actual validation, how much goes into this? You're not really doing this yourself. You're working with partners around the world, I take it. So is it a case of getting them to do some dyno validation of the profile and see how well that kind of matches what your expectations are and then maybe going through iterations? Or are you at a point now where the software is so mature that it's pretty much hitting the mark straight off the grinder?
Yeah, it depends on whether we've ever seen the engine before or whether that it is something that we've done. So if someone was to approach us looking for something for a SRVE, we know that valve train very well. We've got that in the system. We can just start straight down with the how do you want it to behave. We know how those heads work. We can work out what your valve events need to be and design you a real nice package to go with that. But for example, one of our recent ones was for a customer in the States with a McLaren engine that he wanted to take to couple of thousand horsepower turbo grind, and so we'd never seen that valve train before and got really well looked after in the sense that he had some engineering contacts at McLaren who hooked us up with all the valve train geometry from the design. And so we're able to plug that in and then see the whole system and really design a valve motion that we knew was going to spit out a cam that was useful. And you've also then got a really cool team of guys at the other end going, well, we know how this car behaves, and we know that this is what it's going to do. And then we're like, well, we know the turbos you strap into it, so we can say that it'll probably really appreciate X amount more degrees and X amount more lift. Let's see if your valve train can handle that. And we worked back and forth with them to develop a really happy package. And so, yeah, the different ways to approach the system based on who you're dealing with.
In terms of turbo versus naturally aspirated cam grinds, I just want to dive into that just briefly. And obviously, very, very different types of engine here. One of the aspects that we have with a turbocharged engine, which is a kind of a variable that's going to depend on your turbo sizing, is exhaust back pressure, which we don't tend to have in a naturally aspirated engine, certainly nothing to the degree that we're expecting to see with a turbocharger. So how does that affect what you can do in terms of duration and specifically overlap? Do you get to a point if your EMAP is too high and you're using too much overlap that it's actually forcing unburned exhaust gases back into the cylinder and sacrificing the ability to get a fresh air charge in there?
Yeah, it comes down to the efficiency of your turbo system and the RPM you're running at and such. But a lot of modern turbos, you'll end up with a positive differential where that you're actually got more intake charge pressure than exhaust pressure. So if you have too much of that overlap event, you can actually be forcing your intake charge straight out the exhaust. Typically, the problem with that is you're just pushing cold air into that exhaust system, and that pulls energy out of the system straight away as it constricts. At the same time, yeah, if you've got too much overlap and you've got the other option where you've got all that exhaust back pressure, it's going to want to be pushing back against your intake charge. And if you're currently wasting that pressure or letting it out, it's going to be able to revert back that way. So with a turbo engine, we'll typically have a lot less of an overlap event and wider separation on our designs to keep the intake and exhaust from interacting with each other.
I guess in terms of cam design, generalizations are probably pretty difficult. Is it sort of something where as a turbo gets bigger and that relationship between IMAP and EMAP drops away, in other words, we don't have so much exhaust pressure, we can use a little bit more duration and overlap? I mean, you've just mentioned that problem with actually forcing the intake charge straight through the cylinder and out into the exhaust. So obviously there's a balancing act here. But is that the case versus a smaller turbocharger with massively high EMAP where you'd want to keep that overlap period much shorter? Is that kind of the gist of things?
Yeah, that's absolutely the case. And with modern turbos, with their better efficiency and that better ratio between IMAP and EMAP, yeah, you've got the ability to run something that would traditionally be much more similar to a naturally aspirated camshaft because your intake charge has got more energy and it is going to keep moving in the right direction, as opposed to the older, less efficient turbos where the exhaust was always backing up.
Okay. Right, let's move on and talk about the actual equipment for grinding these cams. And you already said you started with a manual cam grinder in Calford, then moved on to CNC. So, I mean, I can assume that the CNC gives much more flexibility as well as much more consistency and repeatability. Is that correct?
Yeah, that's essentially correct. We do get very good consistency and repeatability off the manual grinders, but you're running a copy wheel and a master that's a previously ground, set in stone thing. So you can only grind what you've got waiting on the shelf. basically. Whereas with the CNC, you can design and put a series of numbers in, and it'll spit out that lobe. So if you want to tweak something or change something slightly, or design something totally new, you need that computer aided ability to do that. As in terms of how they function, essentially they're the same thing. It's a large grinding wheel that moves on the manual grinder. The cam moves away from the wheel. On the CNC, the wheel moves away from the cam. But as they're rotating, it's moving in and out and following the pattern of that lobe to cut the material
Hmm.
and give you a lobe shape.
All right. In terms of the actual blank or what you're grinding that profile onto, I mean, I haven't seen it too much for a long time, but in cams where it's not possible to easily get blanks, maybe older engine design, something a little bit special, it's possible to build up the existing cam lobe with essentially weld and then grind that back. Is that correct?
Yes, that is correct. The problem we have there is that you've essentially converted something that was cast into something a lot more like steel, and with your hard overlay, it's going to be a nickel rod that we've gas welded onto your lobe, and it requires sort of a high ester mineral oil to keep that under control. And because it's steel on steel, once again, if your oils get too hot or for a second not changed soon enough and not really well looked after, you're just running a riskier system. But it absolutely can be done, and as long as you're taking good care of your engine, it's still a very reliable system. But when you've got cast iron running on a steel bucket, that's a much safer system to go down, because if you do get a little bit of metal on metal contact, it'll rub but not fret and break down the way that steel on steel does.
So those built up cam lobes, essentially, you'd only go down that path if there was no other option. And obviously, it's not a high volume production technique anyway to be too time consuming. Correct?
As a last resort, yeah. No, it's basically done because it's more cost effective than making a one-off part, complete set of cams. But yeah, it's not ideal. You'd go for a regrind if you could lash the system back up by pulling the base circle down, or you'd go for a blank set of cams if you could find them somewhere, depending on what it is.
Seeing as you just mentioned it, I wasn't going to go down this path, but it is worth mentioning. So a regrind, that's an option for some applications where obviously the lift is essentially the difference between the height of the cam lobe and the base circle of the cam, because it's the base circle that the valve train runs on when the valve's closed. So one way of getting more lift and the ability to add in some more duration is to actually reduce that base circle. There's some knock-on impacts with valve train geometry as well that would need to be considered there. Can you sort of just give us a brief rundown on that? Or how good an option that is?
Yeah, absolutely. It's dependent on the valve train setup. If you're regrinding something like a push rod 4K, you're going to be able to just pull a bit of base circle out of it and set your lash at your rocker, and it's going to be fine. Whereas if it's something like a barra, which is an overhead cam hydraulic lash adjusted roller rocker, once you pull that base circle down, you've essentially changed all the angles in your geometry, and so you want to shim that both sides of that rocker back up at the valve and at the lash adjuster to get it back to what it should be. Otherwise, you're going to end up with a valve train that essentially is a completely different geometry and all asymmetrical at the valve and doing who knows what, because it's going to be based on how much the grinder took off on the day. And so essentially with any regrind, you're limited to how much material there is on the OEM cam and what adjustability you've got in the valve train to get that back to a good standard. If you grind too much off, all of your radiuses are constantly getting smaller and smaller. So over the nose, you're going to be turning from a nice round nose on the top of the lobe to a blade slowly, and there's a point where oil can no longer work in those tight radiuses.
All right, well, let's get on to the preferred techniques and the ones that you're using for the most part, which would be a cast blank that you can then grind a profile onto. I also see from some manufacturers, I don't know if you offer them, billet cams as well instead of the cast blank. Can you talk to us about the pros and cons of those two options? And does it come down to material compatibility?
Yeah, largely. So a cast blank, especially on a flat tappet follower, is superior as it's got the nodular cast iron, so we use grey cast iron, and that nodular graphite that builds up in there acts as a like a bearing and a friction material when those lobes and buckets do touch. And so what you'll see if you try to use steel on a bucket like that is little points of we call it fretting, but it's basically micro welding. When it breaks through that oil, it'll weld briefly and then pull apart and pull that material out. And so we'll see steel cams come in that have been run on a system like that, and they'll just be little chunks ripped out of the lobe surface. Whereas with a cast iron cam, you don't get that. You get that graphite acting as a lubrication barrier and wearing very evenly. As much as you still don't want to go through the oil, it's a much safer system for that style of setup. On the other hand, we absolutely offer billet steel for roller applications and systems where really high stress and really high force is going to be seen. When we're talking about that, we're talking about like the big roller V8s and stuff that are doing, 180 kpsi surface stresses, and at the point where they need to be really high tool steels and stuff and spring steels. Some people will try and tell you that your Mitsubishi Evo is going to need to go to billet steel, but that's not really the case. That's still a nice little roller with a lightweight valve train system. You're not putting a 400-pound on seat spring in that and really hurting that cam. Billet is obviously a much higher loss way of doing a camshaft. You've got to start from a big round blank and machine a lot of material off, and that's a lot of wastage. And whereas a cast system, you get very close to the finished size that you're going to want to need. And the other big thing to factor in is the hardness depth of your material. So with grey cast iron, when you chill cast it, you've essentially got a piece of metal in that casting that's right over the nose of the lobe, and it hardens that material all the way to the core. And that means that when we're grinding something, we can grind a massive 300 degree lobe off that with 12 13 mil lift, and that's going to just clean up that blank. But we can also go all the way down to those little 9 mil lift cams and know that we're still in nice hard material that's going to work well. Whereas when we go to a steel camshaft, induction hardened camshaft that's got a case depth, you've got to be thinking about that while you're building the actual part, and you're going to have to make various size blanks for different bits, because if you grind a little lobe onto it, you've going to essentially gone through that hardening layer, and if you haven't set it up beforehand.
So rather than that hardness going right the way through, it's only just a millimeter or two?
3 or 4 usually,
Okay,
3 or 4 millimeters on a good, it depends on the material, what it can actually do when it gets heated and quenched.
Yeah, okay.
But yeah, if you're going to want to have different billets for different grinds, and that's just less economical again.
Yeah, and obviously there's a cost involved, but on the flip side of that, I can only assume you're probably not going to go to the expense and trouble of having a cast blank made for a one-off application. In that case, a billet, or maybe we talked about the built-up or base circle grinds, would be a more viable financial option for that application.
Yeah, absolutely. And if you had to go to a billet for a single flat tappet engine, then you're going to look at surface treatments like your DLC diamond light carbon, which you will have seen probably on some followers. We do it on some of our bucket for some of our engines, but that is essentially the bare minimum you've got to do to keep those alive. You got to, because it changes that surface from being steel to being something that is compatible with steel instead of being just a steel on steel system.
Yeah, it's really interesting. I think the compatibility of the materials is probably something that is easy to overlook. Certainly, I wouldn't have given it that much consideration. So yeah, it's interesting to get that sort of insight into it.
Yeah, it's huge. And whenever we're designing a new thing, it's what pretty much takes the most amount of time to work out what we're going to do, how customers are going to want these to behave, and how they're going to treat this engine. And so essentially what material we need to start looking at to get that to be the best thing possible for longevity and customer satisfaction at the end of the day.
Makes sense. All right, Thomas, I think we've probably taken up about enough of your time. So let's move on towards wrapping this up, because my brain's about to explode on all of this camshaft information I've just ingested. We have the same 3 questions we ask all of our guests to wrap up. And the first of those is, what's next in the future for you and Calford Cams? What's on the radar?
Yeah, definitely looking to the future's interesting at the moment, I suppose, with a lot of the politics and stuff around green vehicles and electric. where the future of camshafts is, because they're not much use in an electric motor, is definitely a question to look at. And we've recently brought in house all of our own manufacturing and all of our small components and stuff, so we're well tooled up to do lots of things like that. I believe camshafts will be around for a long time yet with the enthusiasts like you and I don't think we're going to want to go away from that smell and that bang of burning some kind of internal combustion, whether it be having to switch to alcohols or potentially with some of the hydrogen stuff. I'll probably get in trouble for saying that out loud, but I think there's probably some cool aspects to being able to still do that, and the hydromechanical systems of internal combustion engine aren't going anywhere anytime soon with the enthusiasts. I imagine we'll be bootlegging cams somehow if we have to, if they get prohibited.
I'd say there's a reasonably long and healthy life left in the internal combustion industry, even though clearly, EV undoubtedly is in our future. But there's definitely enough enthusiasts that I think the demand for camshafts has probably still got it's got a few legs left in it yet.
Yeah, at the end of the day, it's probably only 2 or 3% of people who own ICEs that actually get to the point of looking at doing their camshafts, and those guys are going to be just as enthusiastic about them, whether that there's EVs everywhere or not.
Yep. All right, next question. Given the sort of trajectory you've had in your career and obviously sort of got into Calford pretty much straight away and you've stayed there, but is there anything that any advice you could give to a younger version of yourself or our listeners who are maybe interested in following a similar path that would maybe be interesting, help fast track that career, or maybe avoid any pitfalls you've come across?
I'd probably say the biggest thing was just getting that time to bump elbows with the old boys in the industry. There's an absolute wealth of knowledge out there. Getting that background and getting them to be able to sit down and talk with the people who've gone before in the industry and learn from what they've done and learn from the mistakes a lot of the time, and to be able to build your career from there has been great for me. Just really asking the right questions and getting amongst it and learning how engines work and what they've where they've run into issues and where they've run into limitations, so that you can design and develop things to with the modern materials and modern control systems we can go so much further and really fix some of those problems that are historically been hard to overcome.
Yeah, I think in terms of internal combustion technology, obviously everything continues to march on, but it is really important if you're new into the industry, you sort of think that you know everything there is to know. It's a bit of that Dunning-Kruger effect that comes in, and within reason, there's nothing really new there, and understanding that there are people that have gone before who have probably forgotten more than we'll ever know, and leveraging off their knowledge and trying to avoid making the same old mistakes over and over again, and just having an open mind to accept their knowledge, because a lot of as you mentioned, the sort of the old boys, they're pretty keen to sort of mentor young up and coming enthusiasts as well. So if you've got an open mind and you're prepared to sort of have a chat and listen to some war stories, there's a lot that can be learned. All right, last question for today, Thomas. If people want to find out more about your product, follow along, where are they best to do so?
CalfordCams.com would be our major website, but we also have a good marketing crew on Facebook and stuff now, so we're putting out a lot of what we're doing, and you'll see a lot of the cool engines and drag races and stuff around the world that are running our products and going really good on a day-to-day basis. But also pick up the phone. We're always available on our helplines with technical advice and assistance for anyone from whatever stage you are in your build or your journey into motorsport, and we're happy to help out with setting you up with real cool parts and some world leading advice. And we believe we're got some of the best catalogue and package of what we do in the world. So
Perfect.
Always keen to help with the customers.
Yeah, I mean, I've been a long time user of Calford Cams, and your products have been in the likes of my drag car when I set my world record, and I've had first-hand experience. I mean, it is refreshing to see a New Zealand company that's now just up the road from us, essentially, really operating at a world-class level. So congratulations on all your success to date, and we look forward to seeing more in the future. And hopefully the information in today's podcast is open a few eyes to our listeners on what actually goes into these parts. And again, just coming back to my first point, it's not always a case of just going to the bottom of the catalogue and choosing the biggest, ugliest cam available. There's a lot more that goes into it. So yeah, thanks again, Thomas. Been a great chat.
Thank you.
If you enjoyed this episode of Tuned In with Thomas, we'd love it if you could drop a review on your chosen podcasting platform. These reviews really help us to grow our audience, and that in turn helps us to continue to get more high quality guests. To say thanks, each week we'll be picking a random reviewer and sending them out an HPA t-shirt anywhere in the world. Also, this is a great place to ask any questions you might have too, and I'll do my best to answer them if your review gets picked. So this week, a big shout out to Vlad, who has said, a podcast for car people. There are a few automotive-centric podcasts, and some of them have a really hard time catering for the guys looking to learn something or getting any value out of them, but not HPA. This show interviews people with vast and prestigious backgrounds in the automotive industry and motorsport. Every episode, I learn something that I can apply to my own build and work mindset. The episodes go into how and why people do what they do and what they've learned along the way. There are also names you know or have heard of, so definitely the wealth of information is something you wouldn't want to miss, regardless of your place in the car world. Well, thanks for the kind words there, Vlad. Great to hear that you're enjoying the podcast. Get in touch with your t-shirt size and shipping details, and we'll fire off a fresh tee straight out to you. All right, that concludes our interview. And before we sign off, I just wanted to mention, for anyone who's been perhaps hiding under a rock and hasn't heard of High Performance Academy before, we are an online training school and we specialize in teaching a range of performance automotive topics, everything from engine tuning and engine building through to wiring, car suspension and wheel alignment, data analysis, and race driver education. Now, remember, you've got that coupon code. You can use podcast75 at the checkout to get $75 off the purchase of your first course. You'll find our full course list at hpacademy.com/courses. Important to mention that when you purchase a course from us, that course is yours for life as well. It never expires. You can rewatch the course as many times as you like, whenever you like. The purchase of a course will also give you 3 months of access to our Gold membership. That gives you access to our private members only forum, which is the perfect place to get answers to your specific questions. You'll also get access to our regular weekly members webinars, which is where we touch on a particular topic in the performance automotive realm. We dive into that topic for about an hour. If you can watch live, you can ask questions and get answers in real time. If the time zones don't work for you, that's fine too. You're going to get access as a Gold member to our previous webinar archive. We've got close to 300 hours of existing content in that archive. It is an absolute goldmine. So remember that coupon code podcast75. Check out our course list at hpacademy.com/courses.